So thank you all for coming to the FOSS Mobile Dev Room. Happy to see that the room is quite full. If somebody sees the sign that the room is full, please turn it on the outside. I have no idea how to do that. And Luca is here. He just made a Mastodon post about standing on the stage. And yeah, I guess we are all excited to see Luca's talk from phone hardware to mobile Linux. So please give a round of applause for Luca.
Hi, thank you all for coming. This is my talk from phone hardware to mobile Linux at FOSDEM 2024. So, about me, my name is Luca Weiss. I'm an Android platform engineer at Fairphone, but I'm also open source maintainer and contributor for projects like PostMarketOS, which is a Linux distribution for mobile phones, OpenRazor, an open source driver for Razer products, so keyboards and mice, and a bunch of Linux kind of stuff. And you can follow me on Mastodon if you want. So kind of what is this presentation about? So kind of in order for me to really understand how to port Linux to a phone, I kind of need some understanding of how the hardware works, because otherwise it's really obscure, like what it's doing, etc. Here I'm trying to go from kind of the PCB level using schematics, which are public for Fairphone 4 and Fairphone 5, since I work that's quite useful for me. Also, trying to say like how Linux communicates with the different chips on the SoC, kind of how they, which protocols they use together. And even though you might not have schematics for the device you're working on, generally phone schematics are quite similar because they're all based on some reference design. So even though it might be a bit different, the same concepts generally apply. So let's look a bit at the printed circuit board. So kind of on the left side, you can see, I cannot really show you pointer nicely. You can see a kind of a phone PCB. This is from the Fairphone 2, which I found. The picture with the red arrow, or the chip with the red arrow, the big one, is both the SoC but also the memory, like the RAM, on this device. On newer devices, the RAM is combined with for example, the UFS storage, so the internal storage. This is put on top, called package on package. So they're actually both chips on top of each other. This saves PCB space, so you can make it a smaller PCB, and also saves some signaling or makes better connectivity between the two chips. The chips itself, they're kind of these big array of pins. It's called ball grid array because they are little solder balls, and these are like 1,000 pins or something, and they all connect to the PCB, and that's kind of where everything's routed to. Yes. So then if we go kind of inside the SoC, so this is the one chip that you saw. Here you can see a so-called decap chip. Here the Snapdragon 845. And you can see only kind of the green area here is actually the stuff where Linux is running on. So these are in this example, 8 ARM cores. And they are running kind of the Linux you interact with. But as you can see, there's a lot of other stuff on the SoC. Stuff like the modem is a separate chip. There's a GPU, there's DSPs, etc. There's a lot of other things also running on the SoC. Most of them are booted up at runtime. So Linux is actually loading the firmware into RAM, and then you're booting these chips using some proprietary firmware. The firmware there is not for Linux, but for the separate chips on the device. Unfortunately, for most devices, at least for the hacker community, unfortunately, it is you cannot replace this firmware because it's signed using private keys that are where the public key of that key is burned into the SoC, so you cannot change this firmware. So only the manufacturer can change firmware, but in this way, kind of the manufacturer can also ensure that only trusted firmware is running on a device this way. And all of these firmwares, they're basically just executable files that get loaded. In this example here, for the ADSP firmware, it's just in the hexagon architecture, so it's just a different CPU architecture. But in modern chips, there's also, I think there's some firmware also for different CPU architectures. I think Tensilica or something I've heard, which is used for the video firmware. Now we go a bit into the software side. So kind of you saw there's a lot of stuff on the SoC. But we also need some way to address this, because otherwise we can just run CPU instructions and they don't do much as in communicating with anything else. And so MMIO gets used for this. It's called Memory Mapped I/O. This is kind of, I believe, what most or all ARM chips use, probably also on a lot of other CPU architectures. And you can kind of imagine this, so I guess you're probably all familiar with RAM, so you have like in some address space and you can write to it and you can read from it again. But kind of on with MMIO, on different addresses, you can talk with different functionality. So for example, on some address, for example here on the address 0x100,000, there's the GCC, the global clock controller. So you write to some bits there, and then you activate some clock on SoC. So but just by writing to some addresses and reading from some addresses, you can kind of talk with the rest of the SoC. On the right side, you can see the same representation in device tree. So this is the thing that Linux uses to let the kernel know, or that not just Linux, but to let the kernel know kind of where it can talk with the different components and which drivers it can use for this. So you have a bunch of different nodes for the different addresses, which kind of defines like what component is present at this address. And this needs to be statically defined in the device tree, which is kind of similar to the ACPI firmware on x86. So there it's just kind of a bit differently included. It's not included with the kernel, but it's included with the with the BIOS that you get on the phone. Just to clarify the picture, like the colorful picture on the left side, this is just for illustration. This is not the other two values should match kind of. In the proc.io output you can see, so where you can see the different memory regions, you can also see at address 8 with a lot of zeros to 27FFF. It's kind of the system RAM, so it's actually the address space for the 8 gigabytes of RAM that are on the device. So if you write there, you can read the same value back, as you would expect from a RAM. Don't ask me how this MMIO stuff works. I attended the Free Silicon conference last year. They know kind of how this stuff works. I have no clue. So talk to them if you want to know more. So you saw 2 slides before with the BGA, so the many pins on the device or on the SoC. Even though it's a lot of pins, so it's over 1,000 pins or something on kind of modern SoCs. Of those, most are used for ground or power, so really just not usable for anything like more than ground and power. So on the chipset for the 505, you have 176 kind of GPIOs or useful pins which you can use to do stuff. Even though it might sound like a lot, it's really not much. So if you have, for example, 8 I2C buses and 8 SPI buses and 8 UART buses on the SoC with separate pins each, you already have 80 pins used, and you still want to do a lot more with an SoC. So there's normally a lot of different functionality behind each separate pin on the SoC, which you can switch to in software. This enables flexibility from both the SoC manufacturer, because they can produce one SoC that can be used for a lot of different use cases. But also on the other side, for customers buying this chip, they can use the same chip for also a lot of different use cases. So they can, for example, if they actually need 8 I2C buses, they can actually use them and kind of sacrifice some other functionality by switching to it in software. This is called pin control in Linux, also called TLMM for Qualcomm devices. So you can kind of switch between different functions. So, for example, between I2C, SPI, and UART, you can switch to a different function. And then you get behind the pin, I would say, there's a hardware controller that can actually talk this protocol natively and can do it very power efficiently. On Qualcomm devices, there's up to 9 different functions per pin, but most pins really have something like 2 to 4 functions, and this is just a part of the hardware that you get. In theory, for most pins, you could actually kind of bit bank a protocol on there. So, for example, using a software driver for I2C, you can just have a loop that sets the pins low and high all the time. This generally works for I2C. It's also used in some devices. But it is prone to bad timing, for example, or it's also just, you're using CPU cycles to do something that really a dedicated hardware component can do way more efficiently. On the right side, I grabbed this illustration from the Raspberry Pi documentation. It kind of shows that on the one GPIO that you see, and there's a lot of different functionality behind there. So, for example, in software, you can enable a pull-up regulator. so which is useful for I2C buses, or pull down, or a lot of different interrupt detection mechanisms. So you can just connect a GPIO to an interrupt line from a different chip, and then get an interrupt in there. And yeah, the SoC can tell you very efficiently how this works. Yeah, the bottom left is an excerpt from device tree. So we can see here, for example, the GPIO 155 is just configured to be in the function GPIO, so just normal high-low. Also drive strength of 2 milliamperes and bias pull-up. Bias pull-up here means, for example, the pull-up regulator gets enabled. And you don't have to do this in hardware. You can actually use the one built into the SoC. For the second example, there's the I2C buses. So, for example, for GPIO 24 and 25 on this SoC, for the function called QUP06, which is Qualcomm talk, you can get an I2C bus there. And you need to configure this in software, because otherwise you just kind of get the default pin controller set, which is either set by the bootloader or just kind of the default so GPIO. So if you want to talk SPI, you need to set this correctly. Otherwise, the communication from inside the SoC doesn't go anywhere. So kind of now we know how the pins on the SoC works. So here's an example of, for example, how a speaker amplifier is connected to the SoC. So there's a physical connection between the SoC on GPIO 8 and 9. I think my microphone's falling down. Sorry. Try to fix it again. Okay, perfect. Yeah, so and this is connected to the SCL and SDA pins, so for I2C, on this AW88261 chip, which is just a speaker amplifier. This is used for this speaker connection, so how you output audio on this device. It is used for controlling this amplifier, so kind of telling it some information that it needs to know to be able to properly amplify the audio that's coming. For the audio data will be on the next slide. So here also for GPIO 8 and 9, you can see in the pin control driver, which is the top screenshot on the left, or the black with the black background. Here you can see from the pin control driver that's for GPIO 8 and 9, there's a separate function defined. So then in device tree you can use this function, so QUP02, which is again Qualcomm talk for I2C here. And on the other side, you can see on the I2C pin, or on the I2C bus, there's this Awinic chip defined. So the chip on the hardware has its own node in the device tree, which has, for example, here the I2C address defined, which you can find in the datasheet of the device, or if you're porting downstream Linux, then you find this in the downstream device tree, which is probably most commonly what you use. And also kind of knowing that GPIO 8 and 9 here is the thing called I2C2 in this example. This is also, if you work from just kind of hardware design and data sheets, then you find in the data sheet, but these are most of the time confidential. So you probably just look at the downstream sources if you're porting mainland Linux for it. The speaker gets controlled via I2C, which is a very common protocol. For the actual sound data that you send from the SoC to the amplifier, so it gets to the speaker, you actually use a protocol called I2S, inter-IC sound, sometimes also known as MI2S, which is multiple I2S, so where you have multiple channels. And yeah, you can see here for GPIO 150 to 153 are connected to the I2S pins on the amplifier chip. And yeah, this is how the audio data then gets actually transmitted between the two different chips. Again, you need to configure the pins correctly, so you need to select the I2S functions on these GPIO 150 to 153. The example might be a bit confusing because actually in device tree you set GPIO 6, 7, 8, and 9. This is a bit also because it's not part of the same pin control thing. It's a bit complicated. So I'm probably going to skip this. But yeah, you didn't also need to, because yeah, you've set the I2S output correctly. You still need to send the audio data to the correct I2S bus, because the SoC has, I guess, 5 I2S buses, In this case, the quinary one is used, so kind of primary, secondary, quaternary, etc. And then quinary, so the fifth one. You need to configure this, and then you can really set the sound device tree configuration to send data from the here in this, for example, it's called Q6AFE die, from the quinary basically to the amplifier. And then Linux knows that it actually should use the quinary connection, so GPO 150 to 153. It's sending it to the amplifier, and then Linux also knows that it needs to configure the amplifier correctly to be able to output the audio correctly to the speaker. Here also the I2S interface is actually not handled by Linux itself, but by the ADSP, which is the audio digital signal processor. It's also a thing on Qualcomm, probably also other SoCs, where the main SoC can go into a lower power state if it's just playing audio, because then the separate chip, which is way more efficient, can do this correctly. For microphone, it looks completely different, because why have the same thing for both audio output and input? Here it's going via the WCD9385 chip, which is a Qualcomm chip which is kind of an audio codec there. It's connected via SoundWire, which is a completely different protocol. It's a new standard from around 2014. In comparison, I2S from the previous slide is from 1986, so it's quite an old standard. There's also Slim Bus used on some SoCs, or actually still on the same SoC, but for different use case again, which is a standard from 2007. So in this case, again, as you can imagine, there will be some connection path between the SoC and the amplifier chip, and then from the amplifier, to the audio codec, and from the audio codec to the microphone to get microphone input. So you can see here there's a bunch of pins, GPO 144 to
5 minutes.
Okay. 144 to 158, and 149, and then 158 also. They're connected there. It's a protocol SoundWire. And yeah, there will be just a kind of a physical connection between the audio codec and the microphone, where it can get the data there. And this WCD chip is used for 3 different microphones that are on the phone itself, and also for USB-C audio, where you can actually get an analog audio signal via the USB-C connector out. And here both output and input is handled via this chip. So kind of the microphone also needs to be configured. It works a bit differently here because it's a SoundWire device, so it's different. But kind of you have these two SoundWire devices on the left side. For some reason, they have one for receiving and one for transmitting the data. And then you kind of put them together on the right side as the kind of, again, you have a node for the WCD audio codec, because it's a chip on the SoC that you have. And from this, you reference it, and then you also need to configure the audio path or basically the other way around from the audio codec, so from the WCD chip back to the SoC, so it can receive the microphone data. USB Type-C is quite a cool thing. In the past, micro USB only had kind of the functionality for power, so to charge the phone, data, to transmit a bit of data, some pictures behind it, back and forth, and also OTG functionality to, for example, plug in a keyboard, but it was not really used for much. USB-C can do a lot more. On the 5.5, you can use the connector for USB 2.0, so USB high speed, USB 3.0, which is called super speed, analog audio out via this thing called the audio adapter accessory mode, which is a standard part of USB Type-C, and also DisplayPort out via the DisplayPort alternate mode. So on the 24 pins, you can do a lot of different things. But for actually doing this, you don't just need the SoC and the USB-C connector, but also some other components that actually switch to different components based on kind of what the user plugs in. So for example, for getting analog audio data out of the USB-C connector, so you can just connect USB-C headphones that don't have where the data is not transmitted digitally, but just like analog, just like with a headphone jack connector. So actually the analog signals, they go over the USB 2.0 data pins, so kind of the D plus and the D minus is for the right channel and left channel. And also the two sideband use pairs, which is a part of the USB-C connector. They are used for microphone and ground, or ground and microphone, depending which which headphones you are in, because there's two different standards. And in order that audio data here flows again, you actually need to configure the different chips to handle the data correctly. So I've tried to kind of put in a reasonably understandable format. On the top you can see the WCD codec, so the SoundWire codec that we had before. It has the headphone jack output and microphone input. This is routed to a chip called the OCP 96011. And this is then switching between USB and audio depending on the use case. And this then is routed to the USB-C connector, so you can actually get the data out there. In order to do this, kind of Linux needs to tell this OCP chip, this audio switch, to actually switch between either USB or the analog audio, depending on what you plug in. And this is here called the mode switch in Linux. So in Linux and in device tree, you need to connect them together with some USB-C nodes. There's documentation for all of this, which might not be the best, but if you understand at some point, you maybe understand it. For DisplayPort alternate mode, it's way more complicated because you can there's a lot of different combinations that you can put on the USB-C connector. So some of the super speed pins you can reuse for DisplayPort, either just one lane or 2 lanes or 4 lanes. And for 4 lanes, you actually cannot do USB 3.0 anymore because all of the USB super speed lanes are used for DisplayPort. But you can still use USB 2.0 for this. So there's a lot of different combinations that you can use. The DisplayPort aux channel, which is used for some communication, also runs over some different wires, which also needs to be switched correctly depending on which orientation you plug in the DisplayPort connector, or the USB-C connector, basically. Everything needs to be configured, and if something isn't configured correctly, no data will flow. So then you have a bad time because you don't have DisplayPort out. So kind of device tree, because this talk has been about hardware and device tree. Device tree actually represents hardware. It doesn't represent software concepts. You're not telling Linux to do something, but you're providing Linux with the information that the hardware is made in that way, and then Linux can use this information to actually do the correct things. Keep this in mind when writing device tree or the bindings or the commit messages. Don't write about, hey, this is telling Linux to do this, but you're actually telling, like, you're describing the hardware. If you're adding a new chip, all of the power supplies and GPIOs and everything should be included. Because it represents the hardware. Even if Linux doesn't use them yet, you should include them in the bindings because the bindings represent the hardware. Device tree is also operating system independent, which is really cool because many years ago, like, you wrote kind of really Linux-specific code to make the hardware work. But device tree is operating system independent, so you can use the same device tree for example, U-Boot, which is Caleb's talk, which is coming up in a few minutes. But also, for example, for FreeBSD or whatever. They should be able to use them because it represents the hardware. It doesn't represent Linux-specific things. What did I want to say? It's a great ending. Don't put Linux-specific things in there. They should work if the other operating systems have driver for it, of course. And that's it. Thank you.
Thank you very much, Luca. We have like 2 minutes for questions, so if somebody has a question, please ask now. I will give you the mic.
Thank you for the presentation. Can you tell us if you pick the Fairphone 5 now, or maybe the 4.1, and you actually run a vanilla Linux kernel on it, what can actually work? So you spoke about headphones, mic, things like this. What's the actual state of the Fairphone on vanilla Linux? And also, next question obviously is, like, any plans to make it even more like open in the future?
So right now, like, completely vanilla Linux, a good chunk of stuff is working, but some stuff like display is not working yet. But I have some patches which depend on, like, for display, it still depends on some hack that actually Marijn is working on, hopefully. You can use display, GPU, DisplayPort out over USB-C. You can use modem. You can make, in theory, phone calls without audio because audio is not working yet. So basically the big things that are not working yet is audio is not working yet, camera is not working yet, and probably quite a few more things that you want from a phone. But kind of you can use it as a kind of media machine. If you connect Bluetooth headphones, you can stream via Wi-Fi or 4G or 5G and everything else.
One more question?
Yeah, or maybe quickly plans for the future. I definitely plan on working more on this, but it's also not my full-time job to work on this. I have 1 day a week currently for this. So I can definitely get way more done than without more time. But we will see.
Could you please describe in a few words how do you debug device tree?
Say again?
How do you debug device tree?
I mean, you're not. I mean, to some degree, you're not supposed to debug device tree because it's just a data format that specifies the hardware. Of course, when bringing up hardware, you need to figure out what values to put in there. This is mostly in combination with the Linux driver then, because you're never device tree is just a data format to describe the hardware. So you need something to kind of interpret it and use it that way. So most of the time you are debugging Linux drivers and probably fixing Linux drivers and at the same time fixing your device tree. In a perfect world, you would just write it once and it would be done, and then fix the operating system maybe better.
So that's the time we have. Another round of applause for Luca, please.
Thank you.
And make sure to check out the stands we have for Linux on mobile in building AW. And now we have 5 minutes of break. Don't forget the mic, yeah? And yeah.